welcome students. Now, in this topic, we are going to see very amazing, right? Materials known as superconducting materials. Okay, they are extraordinary in many aspects. Okay, they are what you call. They have some peculiar properties. Okay, where we are seeing now like bullet trains or MRI scannings, magnetic resonance imaging, or bullet trains are usually computers have microsecond switching speeds, whereas we are now seeing some supercomputers having picosecond switching speeds, pico 10 to the power minus 12 second switching speeds. All these are possible due to what are known as the superconductors. Okay, right now in 1911, a scientist called Camerlin Ohms. Camerlin Ohms in 1911. Okay, he was a scientist who could liquefy helium. Helium was the last gas to get liquefied. Helium was the last gas to get liquefied. Okay, and at around minus 268 Kelvin, minus 268 degrees Celsius, at around 4 Kelvin temperature, he could somehow liquefy helium. Okay, after he liquefying helium, it became easy for other scientists to reach near absolute zero temperatures like 1 Kelvin, 2 Kelvin, 3 Kelvin, etc. Okay, because we have liquid helium. Okay, the same scientist Camerlin Ohms was studying how the resistivity of materials change at extremely low temperatures of 1, 2, 3, 4 Kelvin like that. Okay, so he has taken a pure sample of sample of pure mercury. Okay, he was studying how the resistivity of mercury, pure mercury, 100% pure mercury, changes with the decreasing temperature. Okay, for all materials, as resistivity keeps on decreasing, we will be studying that in conducting materials. Okay, as the temperature decreases, resistivity of metals keeps on decreasing. Okay, right. So initially, like any other material, resistivity of mercury also kept on decreasing. But surprisingly, what happened is at one sharp temperature of 4.12 Kelvin, okay, 4.12 Kelvin, the resistivity of pure mercury, okay, resistivity of pure mercury abruptly became zero. Okay, suddenly become zero. This was an extremely unexpected result. Resistivity of a metal becoming zero. When resistivity of a metal becomes zero, right? Resistance of the metal R equal to rho L by A. Okay, rho itself is zero means resistance will be zero. When resistance is zero, right? The energy loss I square RT. Okay, the energy loss I square RT in the material, or power I square R joules losses, also will become zero. Okay, means you send any amount of current through it for whatever time, there is no power dissipation at all. Okay, right? Means resistivity becoming zero. This was a total unexpected result. Okay, he knew that he has found something special and extraordinary, no doubt. But why, if it is simply resistivity becoming zero, he would have called it as an ideal conductor, or a perfect conductor. Okay, ideal gas. Okay, ideal fluid like that. We would have called it as an ideal conductor or a perfect conductor and would have left the matter there only. Okay, but why did he give the special name called superconductor? Okay, means what he later on observed is, apart from resistivity becoming zero, the material is acquiring some special or peculiar properties which are not there when it is in normal conducting state. That is, mercury, in some textbooks you'll find it as 4.2 Kelvin also. Okay, actually, generally we can take it as 4.2 Kelvin, but mercury has two isotopes, Hg199 and Hg204. Okay, one's critical temperature 4.12, other one's critical temperature is 4.16. That we'll see later in isotope effect. Okay, that's why most of the people approximately take it as 4.2 Kelvin. Doesn't matter, in the exam also they are giving. Okay, what is the following which is the critical temperature of mercury? 4.2 they are giving. Okay, whatever it is. Above this 4.12 Kelvin, the mercury is a normal mercury which you and I will see seeing every day. Okay, normal mercury only with normal properties. Okay, but at below 4.12 Kelvin, mercury is acquiring some special or peculiar properties. Okay, resistivity becoming zero is one such peculiar property. Okay, one such peculiar property, it is acquiring some other special properties also. So Camille knows that somehow something is happening to Mercury and it is going in a new phase of matter, hence the name superconductivity. Okay, hence the name superconductivity. Remember, a sample should be pure. Okay, impure mercury again will not become a superconductor. Okay, depending on the type of impurity. This is for a pure mercury at 4.2 Kelvin, resistivity abruptly becomes 0. Okay, right now. Now later on, other people did, and he too tried with the different materials. Different metals or different materials are found to have different critical temperatures. Okay, right? Example: lead. Okay, lead critical temperature is 7.26 Kelvin. Okay, below 7.26 Kelvin, lead is also behaving like a superconductor. Niobium is there. Niobium is a metal which is becoming superconductor at 9.3 Kelvin. Okay, tellurium is another material, another metal which is becoming what you call superconductor 11.2 Kelvin. Okay, zinc becomes superconductor at around 1.1 Kelvin. Uranium also becomes superconductor at 1.2 Kelvin, like that. Different elements have different critical temperature. Tantalum is there. Okay, tantalum is there. Whose critical temperature is 4.4 Kelvin, like that. The temperature below which mercury is losing, or the material is losing its resistivity, that is called critical temperature. Okay, critical or transition temperature. It is usually denoted by TC. Okay, critical temperature below TC, the material, right, is known as a superconductor. Above the critical temperature, at and above critical temperature, it behaves like a normal conductor. It behaves like a normal conductor. Okay, different materials are found to become superconductors at different critical temperatures. Okay, right? Totally, how many elements in the periodic table? About 21 elements in the periodic table are found to become superconductors. About 21 elements in the, not all 92 elements in the periodic table are becoming superconductors. No, only 21 elements. See, usually the valence of superconductors is right 2 to 8. Okay, in the periodic table, second group elements to eighth group elements only can become superconductors. Okay, first group elements are known as alkali elements. Okay, alkali elements never become superconductor. Their valence is equal to 1. Okay, alkali elements never become superconductors. Okay, next one, ferromagnetic materials never become superconductors. Anti-ferromagnetic materials are also not found to become superconductors. Okay, next one, the three noble metals. What are they? Copper, silver, gold. They are known as noble metals. Okay, noble metals like copper, okay, silver, gold. Okay, they also never become superconductors. Okay, alkali, usually superconductors have valency between 2 and 8. Okay, right, 2 and 8. Alkali metals never become superconductors. Ferromagnetic materials never become superconductors. AFM materials, anti-ferromagnetic materials, noble metals, copper, silver, gold, they never become superconductors. Okay, right. So remaining out of remaining, some liquids are there, etc., etc. So in remaining things in the periodic table, about 21 elements are found to become superconductors. Okay, so the temperature at which the material loses its resistivity is known as critical temperature. Okay, different elements have different critical temperatures. Now, okay, you take one normal copper loop. You take one normal copper loop like this and induce some current I in it. Okay, when you induce some current I in it, because copper is of course is a very good conductor, but it has some finite resistivity, and that loop will have some resistance. So I square R losses will occur. That current will become zero very soon. Okay, in fraction of a second, if there is no battery supply. Okay, just induce some current. That current becomes zero within no time. But you take a lead wire. You take a lead wire or niobium wire. Okay, right, made up of lead or niobium. Decrease its temperature to below its critical temperature. Means if you are taking lead, right, reduce the temperature below 7.26 Kelvin. Okay, below 7.26 Kelvin. Okay, right, and induce some current in it. Okay, people have observed that current, because resistivity is zero, that current is found to flow for a very long time. Okay, how long? Nearly people have observed to 11 years. Okay, means once just induce 1 ampere current, up to 11 years the current continues to flow. Decrement in current is extremely small. After 1 ampere, after 11 years, the current 1 ampere current is found to become some 0.9 amperes or 0.895 amperes, like that. Okay, from that they calculated how much could be the resistivity. Resistivity may not exactly become zero. Normally, silver is the best electrical conductor. Its resistivity is around 10 to the power minus 8 ohm meter. Okay, 1.8 into 10 to the power minus 8 ohm meters it is. Okay, resistivity of super, that itself is the best conductor in silver. Okay, whereas resistivity of superconductors is the order of 10 to the power minus 26 ohm meter, means how negligibly small. That's why people practically say it is zero. Okay, negligibly small, infinitesimally small resistivity, means even after flowing for years together, okay, current will not decrease. That 1 ampere current continues to flow for years and years together. That's why currents flowing in superconductors, they are called persistent currents. They are called persistent current. Persistent current means everlasting currents. Okay, they continue for very long time. They persist for very long time. Okay, right? They won't get decreased. Okay, so currents flowing in superconductor loops are called persistent currents. Okay, now this is about the initial thing. What are those other peculiar properties? Now we have to evaluate one after the other. Okay, now it is like this. Okay, now what is the effect of the magnetic field on superconductors? Okay, electric field is not having an effect on superconductors, but magnetic field is found to have some effect on superconductors. Okay, it is like this. You take some material. Okay, you take some material. Okay, you apply some external magnetic field B on it. External magnetic field B or H, because B equal to mu H or mu naught H. Okay, right? B or H, only units are different, that's all. You apply some magnetic field on it and gradually keep on increasing the magnetic field strength. Okay, right? This material is suppose say niobium. Its critical temperature is 9.3 Kelvin, whereas I'll keep it at 9 Kelvin. Below its critical temperature. So below critical temperature, every metal behaves like a superconductor. Okay. So 9.3 Kelvin is the critical temperature. If I put its temperature as 9 Kelvin, it behaves like a superconductor. Now you apply some magnetic field and keep on gradually increasing the magnetic field strength. When you keep on gradually increasing the magnetic field strength, what has been observed is, okay, at one specific magnetic field called critical magnetic field, BC or HC, you can call BC or HC, anything you can take. Okay, right? Even though the material's temperature is below its critical temperature, okay, superconductor gets destroyed or it becomes a normal conductor. That normal conductor transition into normal conductivity occurs at a specific temperature, specific magnetic field. That magnetic field is called critical magnetic field. That magnetic field is called critical magnetic field, BC or critical field intensity, HC we call. Okay, the substance is maintained at low temperature only. Below its critical temperature, means temperature wise it should be a superconductor. But when I applied a specific magnetic field, okay, superconductivity got destroyed. That is, magnetic fields are capable of destroying superconductivity. In the examination, many questions come. Okay, which fields are capable of destroying superconductivity, electric field, magnetic field, like that. Okay, right? Magnetic field is capable of destroying superconductivity. Okay, the field at which the material becomes a normal conductor is known as critical field, BC or HC. Now, critical temperature is a characteristic property of the material. Okay, in the absence of any magnetic field, at what temperature a material becomes a superconductor, that's a characteristic property of the material. But the critical field, that depends on the temperature of the specimen below TC. Okay, critical field BC depends on the temperature of the specimen below TC. Means how? Now look here, its critical temperature is 9.3 Kelvin. Its critical temperature is 9.3 Kelvin. I initially maintained at 9 Kelvin temperature. Okay, 9 Kelvin temperature. Suppose a critical field BC is say 50, say how much? Say 100 Gauss. Okay, 100 Gauss. Right now, I'll decrease the temperature from 9 Kelvin to say 8 Kelvin. Okay, and again I'll repeat the experiment. This time I'll put the superconductor, the material at 8 Kelvin. It behaves like a superconductor. I'll apply magnetic field. That field I'll keep on increasing gradually. Earlier, when the material was at 9 Kelvin, right, 100 Gauss was sufficient to destroy superconductivity. 100 Gauss was sufficient to destroy. Okay, 100 Gauss was sufficient to destroy superconductivity. Okay, Right now, when I decrease it the temperature from 9 Kelvin to 8 Kelvin, 100 Gauss is not sufficient to destroy superconductivity. Slightly more magnetic field is required to destroy superconductivity. Okay, instead of 100 Gauss, now I have to apply some 110 Gauss to destroy superconductivity. I still decrease the temperature from 8 Kelvin to this time directly, say to 5 Kelvin. Okay, and again repeat the experiment. Again, I will keep on applying the magnetic field, keep on increasing its value. Okay, now this time 110 Gauss is also not sufficient. I have to apply some more magnetic field of 130 Gauss or so, something like that. So what do we understand from this? The lower the temperature specimen below Tc, the higher will be the critical field value. Okay, the higher will be the critical field value. Okay, right? The mathematical equation which gives this variation of what you call critical field with temperature is like this. Okay, with temperature it is like this. Okay, Bc equal to, right, Bc naught into 1 minus T square by Tc square. Okay, 1 minus T square by Tc square. Okay, this is how the critical field Bc varies with temperature T. Okay, the higher the temperature, the lower will be, the lower the temperature, the higher will be the Bc value. Okay, right now at T equal to 0 K, at T equal to Tc, you see, at T equal to Tc, what will happen? At T equal to Tc, okay, this is 1 minus 1, 0. So Bc equal to 0. At T equal to Tc, right, you don't have to apply any magnetic field, right? Temperature itself will destroy superconductivity, isn't it? Okay, you don't have to apply any extra magnetic field to destroy superconductivity. Temperature wise, it becomes a normal conductor. Okay, so at T equal to Tc, as expected, Bc equal to 0. Now put T equal to 0 Kelvin. When you put T equal to 0 Kelvin, right, Bc equal to, right, Bc naught, get. Bc equal to Bc naught we get. Okay, means maximum value. What is the curve? Okay, if you draw a graph for this formula, Bc equal to Bc naught into 1 minus T square by Tc square, or in terms of Hc also, right, you can write Hc equal to Hc naught into 1 minus T square by Tc square. Hc equal to Hc naught into 1 minus T square by Tc square. What is the graph for this equation? Okay, right, I take Bc on y-axis and temperature on x-axis. The curve is somewhat like this. The curve is somewhat like this. At T equal to Tc, Bc equal to 0 as expected. Okay, at T equal to 0 Kelvin, at T equal to 0 Kelvin, Bc equal to Bc naught maximum value. Bc equal to Bc naught maximum value. Okay, below Tc, as the temperature keeps on decreasing, critical field value keeps on increasing. And at T equal to 0 K, Bc becomes Bc naught, that is maximum. Okay, now for a material to behave like a superconductor, now earlier if I simply reduce its temperature to below its Tc value, there is no guarantee that it will be a superconductor. Why? If the magnetic field acting on the material is more than the critical field at the temperature, even then superconductor gets destroyed. It behaves like a normal conductor only. It means, right, the material should be inside this curve. Say it is at a point P. It is at a point P means, how do you understand? Its temperature is this much, below Tc only. The magnetic field acting at this temperature, what is the critical field? Critical field should be this much. Okay, critical field should be actually this much critical field should be applied in order to destroy superconductivity. But right, the point is at the material is at this point P means what? The magnetic field acting on it is only this much. So both temperature wise and magnetic field wise, it is inside this curve, so it behaves like a superconductor. Means materials to behave like superconductors, they should be inside below this curve. On the curve also will not. That's also that question has come once in UPSC. Okay, he has given the graph and said, right, at which point? On the curve, beyond the curve, below the curve, or on the curve, like that. Okay, it is below the curve only they behave like superconductors. On the curve and outside the curve, they behave like normal conductors. Okay, they behave like normal conductors. So for a material to behave like a superconductor, now two conditions must be satisfied. One is its temperature should be below Tc. And second one is, if any magnetic field is acting on it, that magnetic field should be less than the Bc value critical field at the temperature. Okay, the mathematical equation for this curve is Bc equal to Bc naught into 1 minus T square by Tc square. Some problems also will come on this. He will give you what you call Bc naught value, he will give you critical temperature. At so and so temperature, what is the critical field? A straightforward question will come. Okay, right? Once a question has come, critical field, critical temperature for lead is 7.26 Kelvin. Okay, right? Its Hc naught value is 10 to the power 5 ampere per meter. Okay, at T equal to at T equal to 5 Kelvin, what is the critical field Hc? Okay, Hc equal to how much? This question was asked once in a UPSC exam. Okay, right? So simply straightforward substitution. Okay, now I'll use Hc equal to Hc naught into 1 minus T square by Tc square. Hc equal to some 10 to the Hc equal to some 10 to the power 5, right, into, right, 1 minus T square by Tc square. At what temperature is asking? At 5 Kelvin, what is the critical field is asking. So 5 square is 25 by, right, Tc. Tc is 7.26 Kelvin. Tc square 7.26 whole square. Approximately, I don't want to use any calculator. I want to arrive at the result very quickly. I'll take 7.26 whole square as some 50, slightly more than 51, slightly around 51, something like that. Okay, but I take it as 50 for such that it becomes easy for me to simplify. So it is simply 1 by 2. 1 minus 1 by 2 is 1 by 2. So 0.5 into 10 to the power 5. Okay, ampere per meter will be the critical field at the temperature. Any answer which is close to 0.5 10 to the power 5 will be very close to 0.5 10 to the power 5 will become your answer. Okay, right? So we can avoid using calculators by making the appropriate approximations. Okay, right? So this is what you call the effect of magnetic field on a superconductor. On a superconductor, magnetic fields are capable of destroying superconductivity. Okay, right? Next. Next, it is Meissner effect. Meissner effect. Okay, right, now you take a material. Okay, initially this material's temperature is greater than the critical temperature. Okay, when the material is greater, as temperature is greater than Tc, okay, it behaves like a normal conductor. Okay, right? You take lead or mercury only you take. Okay, put its temperature as at 6 Kelvin. Critical temperature is 4.2 Kelvin. No, at 6 Kelvin it behaves like a normal conductor. Now on that mercury sample, you apply magnetic field. Okay, these magnetic lines of force, magnetic field lines will be able to pass through the interiors of the specimen. Okay, will pass through the interiors of the specimen. Okay, right? When the material is in normal conducting state, right, that is T is greater than Tc, and when you apply any magnetic field on it, magnetic field lines will be able to pass through the interiors of the specimen. Okay, right, now this is a situation to every material. Let the material be diamagnetic. How many materials are there? Okay, dia, para, ferro. Okay, ferro, anti-ferro, ferri, super. There are special cases of ferro only. Okay, so let it be diamagnetic material or paramagnetic material or ferromagnetic material. In whichever material you apply magnetic field lines will be able to pass through the interiors of the specimen. This is a plastic material, plastic pen. When I apply some magnetic field, magnetic flux lines will be able to pass through the interiors. Okay, if it is dia, somewhat less number of lines of force will pass through. Para means slightly more number of lines of force will pass through than what are there in outside. Okay, if it is ferro, still maximum more number of lines of force will be present inside the material. That's it. But magnetic field lines will be able to pass through every material. Okay, right? So this is a situation, right? When now what happens in this situation, I'll apply the magnetic field, I'll keep it that way, but I'll keep on decreasing the temperature. Okay, when I keep on decreasing the temperature, what happens is, okay, at one temperature it becomes a superconductor. The moment it becomes a superconductor, all the flux lines which have been passing through the interiors of the specimen suddenly get expelled or pushed out of the interiors. Suddenly they get pushed out of the interiors like this, such that not even a single line of force will be able to pass through the interiors. Okay, right? Not even a single flux line will be able to pass through the interiors of the specimen. The moment it becomes a superconductor, right? The moment it becomes a superconductor, all the magnetic flux lines which have been passing through the interiors of the specimen till then will get suddenly expelled out or pushed out of the interior. This happens at T less than Tc, or the material is in superconducting state. Material is in superconducting state. This happens suddenly, not gradually. Okay, the sudden expulsion of magnetic flux lines from the interiors of the specimen, the moment it becomes a superconductor, is known as Meissner effect. Right? The sudden expulsion of magnetic flux lines from the interior specimen, the moment it becomes a superconductor, is known as Meissner effect. Okay, means in Meissner effect, all the flux lines have been pushed out. So what is B value inside? B is nothing but number of magnetic lines of force passing through unit area of the material, isn't it? Okay, that B value inside the material will be equal to 0. The B value inside the material is equal to 0. Right? This sudden expulsion is known as Meissner effect. Now, in magnetic materials, in magnetism, we will have a relation between the three magnetic field vectors. Okay, B bar equal to, right, mu naught into M bar plus H bar. Okay, this is the relation between the three magnetic field vectors. B is magnetic field strength, Weber per meter square units. Okay, mu naught is permeability of free space, 4.24 - 7. Okay, M is intensity of magnetization, units are ampere per meter. H is magnetic field intensity, units are again ampere meter or ampere turn per meter, we call it. Okay, right, so B equal to mu naught into M bar plus H bar. Now that B value inside the material itself is becoming 0. Okay, there is not even a single flux line passing through the interiors, isn't it? So implies what? Mu naught into M bar plus H bar is equal to 0. Mu naught is a constant, it cannot be 0. Implies what? M plus H equal 0, or M bar equal to minus H bar, or the ratio M bar by H bar, as we all know, is called magnetic susceptibility chi. Okay, it is called magnetic susceptibility chi. Chi equal to M bar by H bar is equal to -1. Okay, this is a very, very peculiar result. Okay, this also has come recently in what you call engineering services exam, right? Bullet trains are bullet trains have the superconducting materials used. Okay, which peculiar property of superconducting materials is used in bullet trains? Okay, this one. Okay, susceptibility. The moment you find susceptibility negative, understand that it is a diamagnetic material. Out of all magnetic materials, only diamagnetic materials have negative susceptibility. Okay, but normal diamagnetic materials like copper, silver, gold, okay, diamond, water, they're all diamagnetic materials only. Glass, quartz, etc. Okay, they're all diamagnetic materials, right? Their susceptibility will be minus 0.00001. Okay, 0.401 negative value. That is, they are around -1 into 10 to the power -5. Diamagnetism is a very weak effect. Okay, diamagnetic susceptibility is negative but extremely small. How much? -0.401 or -1 into 10 to the power -5. Okay, the best known diamagnetic material known to man is bismuth. Even its diamagnetic susceptibility is -1.7 into 10 to the power or -17 into 10 to the power -5 it is. Okay, -17 into 10 to the power -5 is the diamagnetic susceptibility of bismuth, which is known as the best diamagnetic material. Okay, right? Even the best diamagnetic material susceptibility is also -17 into 10 to the power -5 means -0.00017. What else? We have what here? Susceptibility chi equal to negative means it is understood diamagnetic. -1 means nearly 1 lakh times more, 10 to the power 5 times more than normal diamagnetic susceptibilities. So they are extremely powerful. Diamagnetism means what? Diamagnetic materials get repelled away from external magnetic fields. Okay, with that weak susceptibility, with extremely small susceptibility, bismuth get repelled away from magnetic field in a very powerful manner. Imagine superconductors are having 1 lakh times more negative susceptibility than them. Their repulsion power, the force which they repelled is tremendously big. Okay, they get totally repelled away from external magnetic field. That's why this concept is used in magnetic levitation. Common man's name is maglev trains, people call magnetically levitated trains. Okay, right? The bottom part, I can say that, bottom part becomes superconductor, bottom part of the train is superconductor, the track is a powerful electromagnet. Okay, due to the extremely high repulsion between the magnetic field and superconductor, the entire train, whatever maybe its weight, it will be floating in air. Okay, floating in air means don't imagine that the train will jump out of the platform to this height and keeps on going like that. No. Okay, Then 1 mm, 2 mm is sufficient. No, there should not be any friction between the track and the train. That's all. Okay, friction. It is not. There is no friction. There is no contact. It's like an aeroplane only. Okay, aeroplane flying in air and what you call train going in air on track. Both are similar. No, that's why bullet train speeds are as high as aeroplane. Okay, technically, of course, some aerodynamic other properties will be there. Okay, whatever it is, that trains can have what you call move speeds with they move with speeds of 600 kilometers per hour, 700 kilometers per hour, very close to the what you call speed of aeroplanes. Okay, so this magnetic levitation property, right? It has come because diamagnetic susceptibility of superconductors is -1. This is a peculiar property. This is a peculiar property. Okay, diamagnetism. Okay, the diamagnetic materials are independent of what you call diamagnetic susceptibility is -1. That is perfect diamagnetic. That's why superconductors are perfect diamagnetic materials. Okay, superconductors are perfect diamagnetic materials. In what you call many entrance examinations, superconductors are question comes like this. Okay, ferromagnetic, paramagnetic, diamagnetic, perfect diamagnetic. It's not ordinary diamagnetism. Okay, it is perfect diamagnetism. Okay, so superconductors are perfect diamagnetic substances. Okay, perfect diamagnetism and perfect conductivity are two independent properties of superconductors we call. Okay, perfect diamagnetic substances. Perfect diamagnetic substances. Okay, perfect diamagnetic substance, not ordinary diamagnetism. Okay, so susceptibility chi equal to -1. Okay, this effect is known as Meissner effect. Okay, this effect is known as Meissner effect and it is a reversible effect, remember. Okay, it is a reversible effect. Okay, one of the very few reversible effects in physics. It is a reversible effect. Okay, what is the meaning of reversible effect? You start from this point. You take the material normal state. You apply some magnetic field, flux lines will pass through. Then keep on decreasing its temperature. The moment it becomes a superconductor, all the flux lines will suddenly get pushed out of the interiors. Okay, from here you can go to this situation, or directly you can take a material which is in superconducting state and apply magnetic field on it. Okay, when you apply some magnetic field on it, not even a single flux line will be able to pass through. Of course, that magnetic field should be less than its critical field. Remember, okay, right? So if critical field is 100 Gauss, you apply 200 Gauss on that superconducting material, its superconductor gets destroyed. It becomes a normal conductor. All the flux lines will pass through. Temperature will be less than T7. Okay, this magnetic field should be less than the critical magnetic field of that. That should be taken care of. Okay. So you take what we call a superconductor, apply some magnetic field on it, not even a single flux line will be able to pass through. Okay, keeping that magnetic field like that, start increasing its temperature slowly. Okay, right, at one temperature, it automatically becomes a normal conductor. The moment it becomes a normal conductor, all the flux lines again will start penetrating through the material. Okay, will start going through the interiors of the specimen. Okay, from here you can come here, or from here you can go there. Okay, it is known as a reversible effect. It is called a reversible effect. Okay, right now this is next one observed thing. Okay, second one is you take one copper wire. Okay, copper loop and put some current on it. Okay, whenever there is some current in a loop, what happens, right? It produces some magnetic field. It behaves like a dipole. It produces some magnetic field. What is the magnetic field at the center of the loop? Center of the loop B equal to mu naught I by 2r. This is nothing but our Weier's-Sauer law application. Okay, first what you call B due to a thin long straight wire, B due to a bent wire. Okay, B due to a circular loop. B due to a circular loop at its center is mu naught I by 2r. Okay, this much B value will be there. Okay, B is nothing but number of lines of force passing through unit area. Okay, the total number of lines of force passing through the entire loop, okay, that is called magnetic flux phi B. Phi B equal to B into, because it is a perpendicular case, I am directly writing B into area of the loop, okay, pi r square. B is number of lines of force per unit area into area will give you total number of lines of force passing through the entire loop. That is phi B. It is called magnetic flux. So B equal to mu naught I by 2 pi r into pi r square. Into pi r square. You will get phi B here. Okay, you will get phi B here. Phi B equal. Now, current is an analog quantity. Okay, you can change current continuously as you like. Okay, you can put 1 ampere, you can put 1.1 ampere also, or you can put 1.11 ampere, or you can put 1.12 ampere, 1.111 ampere, like that. Okay, right? Current can be changed, can be increased or decreased continuously. Current can be increased and decreased continuously. When you are increasing and decreasing current continuously, what do you expect about 5B? 5B also should increase or decrease continuously. 5B also should increase or decrease continuously. Okay, because I is continuous, okay, B will be continuous, and B is continuous, 5B also is expected to be continuous. Okay, but what has been observed is, even though you are changing the current continuously, even though you are changing this current continuously, 5B is found to change in quantized form. Okay, 5B is not changing continuously. 5B is found to be in the multiples of a fundamental unit. Okay, fundamental unit, that is, 5B is not changing continuously. 5B equal to n phi naught. N phi naught means the field inside, sorry, the flux inside the loop is either 1 phi naught or 2 phi naught or 3 phi naught or 4 phi naught, that's all. It is not changing continuously. This is known as quantization of magnetic flux. Quantization means changing in some fixed amounts only. Okay, just like currency is quantized, you and I can give and take money in terms of what's called 1 paise, 2 paise only. No, can anybody give anybody 1.2 paise or 1.234 paise? No. Okay, currency on paper is quantized in terms of 1 paise in India, but outside practically, do we have 1 paise coin now? Okay, no. 20 and 50 coin also is not there. What is the minimum now? 1 rupee coin. So any give and take transition between two persons in terms of cash is only in the multiples of 1 rupee only. No, I'm not finding even 50 paise coin or 25 rupee coin in India now. Okay, right? So that 1 rupee now has become the minimum quantum of currency in India. Okay, similarly, the flux enclosed, flux inside the loop is either 1 phi naught or 2 phi naught or 3 phi naught, like that. Okay. Sorry. Okay. Right? What is that phi naught? That phi naught, phi b equal to, okay, n h by 2e. N h by 2e. That is, this unit of what you call the quantum of magnetic flux is phi naught equal to h by 2e. Its value is 2.09 into 10 to the power minus 15 Tesla meter square. Okay, 2.09 into 10 to the power minus 15 Tesla meter square. This quantum of magnetic flux is called, right, fluxon. Okay, the quantum of magnetic flux is called fluxon. Remember the expression for fluxon, it is h by 2e. h by 2e, 2.09 into 10 to the power minus 15 meters. Okay, this also can be asked in many examinations. Okay, right? A fluxoid, some people call it as fluxoid also. Yeah, quantum of matter, quantum of photon, light is light. Photon means light. Okay, in photon is quantum of light. Fluxon is quantum of magnetic flux. Okay, right? So this is called flux quantization. This aspect is called flux quantization. Again, this is also, right, quantization. This is also a special property of superconductors. Only in superconductors, flux is found to be quantized in the multiples of the fundamental unit called h by 2e, fluxon. The flux through the superconducting loop is either 1 phi naught or 2 phi naught or 3 phi naught, like that. Okay, this is called flux quantization. Okay, this is one more special property observed in superconductors. Okay, next one is what is known as Silsby's effect. Okay, or critical current density JC. Okay, Silsby's effect or critical current density JC. Silsby's, name of a scientist. Silsby's effect or critical current density. Critical current density JC rate. Okay, now you take one, what you call copper wire. Okay, the axis is passing through the axis is like this. Okay, right, radius of the wire is suppose a Kepler. Radius of that wire is a Kepler. Okay, and you set up some current I through it. Whenever some current I is passing through a metal wire, so some metal wire, it produces magnetic field around it. That's why the effect was discovered by whom? Just try to recollect. Okay, whenever there is some current in a wire, it produces magnetic field around it. Okay, that effect was discovered by Ørsted. Okay, that effect was discovered by Ørsted. Okay. Now, due to the means of what will be the direction of the magnetic field? Direction of the magnetic field is given by Ampere's right hand rule. Hold the current carrying wire in your right hand with thumb in the direction of current. Curling right hand, 4 fingers will give you direction of the magnetic field. Okay, that is magnetic flux lines will be like this. Okay, magnetic flux lines will be concentric circles like this. Concentric circles like this. Hold the current carrying wire in your right hand with thumb in the direction of the current. The curling right hand 4 fingers will give you direction of the magnetic field lines. Okay, means the magnetic flux lines will be like this. Okay, now this is known as Ampere's right hand rule. Okay, because Ampere said don't try to hold the current carrying wire in your right hand. Okay, let Ampere do that. What happens if you hold the current carrying wire in your right hand? Right? So be careful. It is only for demonstration purposes we say like that. Okay, right? So don't hold current wires in your right hand like this. Okay, to prove Ampere's law, we'll go to Ampere himself directly. Okay, right? So it is like this. Now, what is the magnetic field? What is the magnetic field at a distance r from the wire? Okay, at the distance r, what is the strength of the magnetic field at a distance r? This is given by Biot-Savart law. Okay, this is given by Biot-Savart law. Okay, according to Biot-Savart law, whenever there is some current in a wire, it produces a magnetic field at a distance r given by mu naught I by 2 pi r. Mu naught I by 2 pi r. R is the perpendicular distance of the point from the axis of the wire. From the axis of the wire, B equal to mu naught I by 2 pi r. Okay, I'm taking all these results from the electromagnetic theory. Okay, right? These are all fundamentals of magnetostatics, right? B equal to mu naught I by 2 pi r. Now, what is the magnetic field on the surface of the wire? On the surface of the wire means the surface of the wire is at a distance capital R, which is nothing but radius of the wire from its axis. So, right, on the surface of the wire, how much is the magnetic field? How much is the magnetic field? Simply replace this R with the radius of the wire, capital R. That is the amount of magnetic field that will be acting on the surface of the wire. Okay, right, now what happens is, this is the situation for normal copper wires. Okay, now I'll take one superconducting wire. Say niobium wire I will take. Okay, niobium's critical temperature is 9.3 Kelvin. Okay, I'll reduce the temperature of this wire and I'll put it at 7 Kelvin temperature. So at 7 Kelvin, niobium behaves like a superconductor. Okay, so when it behaves like a superconductor, resistivity is 0, resistance is 0. So what do I feel? I can send any amount of current through it. I can send any amount of current through it. Okay, so what do? I'll start setting up some current and keep on increasing its value. Keep on increasing its value. When the current reaches a critical value, that critical current IC, okay, the wire will lose its superconductivity and becomes a normal conductor. Okay, and becomes a normal conductor. This effect is known as Silsby's effect. This effect is known as Silsby's effect. This critical current per unit cross-sectional area of the wire, is called critical current density JC. Okay, this critical current per unit cross-section area of the wire is called critical current density JC. Means what? Because it's a superconductor, now what do you understand from this? You cannot send any amount of current you want through superconducting wires. Okay, when the current passing through the superconductor wire reaches a critical value called critical current, okay, right, the superconductivity of that metal automatically gets destroyed. Okay, it becomes a normal conductor. When it becomes a normal conductor, why will I use lead wire or what you call niobium wire? Copper wire, silver wires are best. No, copper is there, aluminum is there, which are excellent conductors normally. Okay, the speciality of superconductors is in superconductivity. As long as they behave like superconductors, they are useful to us. Okay, but right, even though they are behaving like superconductors, even though I maintain the temperature at very low temperature of 7 Kelvin, okay, when the current passing through the superconductor reaches a critical value, it is losing its superconductivity. What is the reason for this? Means, see, I am not applying any magnetic field. I am not applying any magnetic field. I have simply taken the niobium wire, kept its temperature 7 Kelvin so that it behaves like a superconductor and started sending current through it. Whenever there is some current passing in a wire, immediately that magnetic field B equal to mu naught I by 2 pi r will be acting on the surface of the wire without whether I like it or not, that field will come. Okay, whether I like it or not, that field will come, that will be acting on the surface of the wire. Okay, as I keep on increasing current value, right, this material will have one BC value, isn't it? One BC value at, for this temperature we have seen now, right? The magnetic field variation, critical field variation of temperature is like this. So at 7 Kelvin temperature, niobium wire will have some critical field BC. Okay, so when current is increasing, when current reaches a critical value IC, the corresponding magnetic field will be just equal to BC, that is critical field of that material at the temperature. What happens? Superconductivity gets destroyed and it becomes a normal conductor. Okay, it becomes a normal conductor. So what does that mean? I cannot send any amount of current to superconducting wire. There is a limit also. Okay, that critical current per unit cross-sectional area of the wire is called critical current density. Okay, critical current density means, now tell me, a material has to behave like a superconductor means now 3 conditions must be satisfied. What are they? First of all, its temperature should be less than its critical temperature. If any magnetic field is acting on it, that should be less than the critical field BC. If any current is passing through the material, it should be less than the critical current IC. When all these 3 conditions are satisfied only, the material will behave like a superconductor. Means I can draw a 3-dimensional picture like this. I can draw a 3-dimensional picture like this. Okay, when will a material behave like a superconductor? This is temperature. This is critical field. Okay, this is critical current density JC. Critical current density JC. Okay, so for first critical field and temperature, we got something like this. Now this third additional condition also has come. The current density should be less than the critical current density. Okay, means it is like this. Okay, only when what you call the material is inside this loop. Okay, inside this, it behaves like a superconductor. Outside this loop, it behaves like a normal conductor. Okay, 3 conditions must be satisfied. Okay, now on what factors does this critical current density depend? Critical current density depends on what factors? Tell me. Okay, right? Critical current density JC or IC, critical current depends on what factor? Critical current is related to BC. BC is related to temperature of the specimen. Okay, the lower the temperature of the specimen, the higher will be the critical field value. So at 7 Kelvin, some critical field is there. For some small current, right? It has lost its superconductivity. But when I decrease the temperature from 7 Kelvin to suppose say 2 Kelvin, okay, the lower the temperature, the higher will be the critical field. BC value will be high. When BC value is high, I can send more current through the superconductor. So this critical current density depends on the temperature of the specimen below TC. That is first point. Second point, if there is any external magnetic field acting on that wire, it depends on that. So critical current density depends on the temperature and any external magnetic field acting on it. Suppose say I have kept it at 7 Kelvin. At 7 Kelvin, its critical field is suppose say 100 Gauss. So the critical field, when current is having some value, this mu naught IC by 2 pi, if it becomes 100 joules, it loses its superconductivity. That is known as critical current, corresponding critical current density. Now, already I have applied external magnetic field of 60 Gauss. Okay, 60 Gauss. Now, the magnetic field due to this current, if it is just equal to another 40 Gauss, 60 plus 40, the total magnetic field on the wire will become 100 Gauss, material loses its superconducting. So, critical current density depends on the temperature of the specimen and any external magnetic field acting on it. Okay, these are some observed aspects of superconductivity. Okay, currents in superconductors are called persistent currents. Okay, second one, magnetic fields are capable of destroying superconductivity. Magnetic flux enclosed by superconducting current rings are found to be quantized. Okay, next one, we have seen is critical current density JC and Meissner effect, that is perfect diamagnetism. Okay, now all the topics which you have discussed is only for what are known as type 1 superconductors. Okay, later on, after 1911, 1920s and 1930s, okay, people have found as another type of superconductivity alloys. Mostly they are alloys. Alloys means mixtures of metals. In mixtures of metals, a slightly different type of superconductivity has been observed. So now superconductors are divided into 2 types. Okay, one is type 1 superconductors and type 2 superconductors. Type 1 and type 2 superconductors. type 1 and type 2 superconductors, or people call them as soft and hard superconductors also. Okay, type 1 is soft superconductor, type 2 is hard superconductor. Okay, what all properties we have seen till now, okay, are for type 1 superconductors. Okay, special type of superconductivity, type 2 superconductor has been observed mostly in what you call metals. Okay, 99% it is in mixtures of what you call alloys. Okay, mixtures of metals, right? That aspect will continue in the next video. Goodbye till then. Thank you.